Good afternoon, everyone. Welcome to the ninth lecture of structure analysis course. Let me share my screen first. I hope the screen is visible to everyone. Let's get started. So, this is the ninth problem solving session related to structure analysis course provided by NPTEL. I am your teaching assistant for this course. My name is Pranam Mahajan. I am a PMRF scholar in Structure and Engineering Division from IIT Madras. So, till now, what we have covered. So, previously, we have started with the analysis of determinate structure. So, from week 1 to week 5, we have solved the problems related to statically determinate structures. Then we have seen the problems related to influence line diagram, wherein moving load when moves over the structure, how it will affect. So for the statically determinate structures, we have started with using the equilibrium equations and determining the reaction at different points of the beam, and then determining the shear force and bending moment diagram at different points of the section. Then we have moved to the truss members. In truss member, what we have seen that a truss is a two force member. It can only take the tension as well as the compression force. Bending moment is not is not applied over the truss member. That's how it differentiate between a frame member as well as a truss member. So to determine the forces in the truss member, we have utilized method of joints and method of sections. Then in next week, we have moved to determining the horizontal as well as the vertical deflection in the trusses using the principle of virtual work and unit load method, wherein we have determined the horizontal and vertical deflection at the required point using by the application of the unit load at that particular point, and then applying the principle of virtual work in which the internal work done will be equal to the external work done, and then determine the deflection at that particular joint. Then we have also utilized the concept for determining the deflection for beams and frames. So we have used the moment area method, conjugate beam method, and the virtual work method to determine the values of deflection in statically determinate structures. So this is first part of the structure analysis course that we have completed. Then we have moved to the moving loads. So whenever a train passes over a beam as well as over a truss, how the reactions, bending moment, shear force varies along the length of the section, that is determined using influence line diagram. So influence line diagram, we utilizes Mueller-Bridges law principle, in which we will see that how the deformations, or sorry, the reactions, shear force and bending moment is varying along the length of the section due to the moment of moving load along the length of the beam, and how we can equally distribute the moving load at particular joint to determine the maximum bending moment and shear force at that particular joint. Then we have moved to the second part of the structure analysis course, which is the analysis of statically indeterminate structures. So we have started with the introduction of force and displacement method, where in force method we have seen that how we can utilize the concept for flexibility matrix, and in displacement method we have seen how we can use the stiffness matrix. So stiffness and flexibility are inversely proportional to each other, and then to determine the forces in the statically indeterminate trusses, we have utilized the method of consistent deformation. So method of consistent deformation is same, we have called it as force method. So first, we have in previous week we have utilized this concept in trusses, and now in this current week we will utilize this concept for beams as well as for the frames. Okay, so what are the various steps that are required for the analysis of the statically indeterminate structures using the method of consistent deformations? So, first of all, you are required to calculate the degree of static indeterminacy, whether in truss or whether in beams. So, what you will do in truss, you will use ds is equal to m plus r minus 2j, and using that equation you will determine the value of that degree of static indeterminacy. Whereas in beams, how you will define that, you will determine the total number of unknowns minus the number of equilibrium equations. So you have three equilibrium equations. When you subtract the total number of reaction unknowns from three, you will take to know the value of degree of static indeterminacy. Then you will select the redundant or unknowns in the structure. So whether it is externally indeterminate or it's internally indeterminate, you will select based upon that. So then you will solve the determinate structure after removal of all the redundant forces in the member. Then you will calculate the value of uh, either slope or deflection at that particular point, and then you will solve for the redundant force without the application of external force over the whole truss or beam element, and then you will utilize the concept of consistency equation, and then you can say that suppose what kind of consistency equation you use. So at slope at particular joint will be equal and opposite along the length of the continuous span of the beam, whereas the deflection at that particular point will be equal to zero. So if you add the deflection due to the static determinate stress and the due to the redundant force, so their sum will be equal to zero. So this is how you utilize the concept of method of consistent deformation or force method. So in this week, we have also covered the three moment equation. So three moment equation is generally used when you have continuous beam along the length, and that is not determinate and it is indeterminate. So to determine the value of moment along the different uh, support points, you utilize the concept of three moment equation. So let's have a look at how the equation for three moment equation is derived, and then we will try to solve few problems on that as well as uh, uh, for the beams also, considering the method of consistent deformation using unit load method. So let's get started. So suppose you have a beam element. Now you will apply the different kinds of loading that are there over the structure. Okay, so let's apply the journal loadings. Before that, we will apply the reactions. So at end there is a hinge reaction. In between, roller reactions are there or roller supports are there. Let's extend this beam further. Now apply the loadings that are there. So you have uniformly varying load along the length of the structure. So this is the UVL. Then you have two concentrated loads over the span. Then again you have a UVL. and then a concentrated load at the end. So let's mark these supports as A, B, C, this is D, and this is E. Now to solve that, since these are the end moments, end support, so here the moment will be equal to 0. So ME will be equal to 0, MD will be equal to 0. So only concern in this uh, continuous beam for you will be the span ABC. So considering the span ABC, what will be having? So if we consider the span ABC, let me draw it again. So suppose you are having this loading, and these are your these are the loadings on span BC, right? So in this, what they have said that apply internal hinge at the joint points. Okay, so these are our joint point or the at the supports. So internal hinge is provided. So here the reaction will be A, B, and C, and the deflection in this part will be like this. Will be like this. Okay, and the slope will be like this. Yeah. So this slope will be theta BA, and this will be theta BC. If we talk about the bending moment diagram for this beam, so it will be, we will just make a journalized bending moment diagram, not for, okay. So we are making the journalized bending moment diagram, not for this concentrated moment as well as the uniformly varying load. So in this, the area of the bending moment diagram will be AAB, and here it will be ABC. So now the distance from the end will be here. Here it will be this H. To determine the moment of the area, it will be HAB, or we can say this distance is the centroid of the area. This will be HBC. Okay. Now, due to this hinge points, A, B, C, so the moments here will be, this will be your A, MA, then this will be your MB, and this will be your MC. Okay. So if we draw this bending moment diagram, it will look like this. Let this will be MA, this will be MB, and this will be MBC. Okay, so this will be your MA, MB, and MC at point A, B, and C. So now we will apply here the moment area method. So what moment of area method says that the deviation of any point B relative to the tangent drawn to the elastic curve at other point A in the direction perpendicular to the original position of beam is equal to the moment of B with respect to M upon AI diagram between A and B. So it says that if you are deriving the deflection from point B with respect to the point A, so that will be equal to the moment of area of the M upon EI diagram with respect to B. So that means your delta BA will be equal to AAB into HAB. Now this is my moment divided by EI will give me the deflection at that particular point. So now also we will know theta BA will be equal to delta BA upon L. So it will be equal to AAB HAB upon EAB IAB LAB. Okay. Now if we take the redundant part of that beam, so we will have in the bending moment as MA, MB and MC. MA, MB and MC. So if we have to determine the theta of this part, so this theta BA will be equal to 1 upon E, 1 upon LAB into MA into LA upon EI, EA, or it should be E only, IAB into what will be the distance? It will be LAB upon 2. So this is for the rectangle part of the trapezium, and for the triangle part it will be 1 by 2 into MB minus MA into LAB divided by EIAB, and it will be acting at a distance of 12 by 3. 2 into LAB divided by 3. If we rearrange this, what we will get? We will get MAB, MA, LAB divided by 6 EAB, IB plus MB and LAB upon 3 EAB, IB. Okay. So similarly, we can also derive for theta BC. And it will be also equal to MB, MC, LBC divided by 6 EI plus MB, LBC divided by 3 EI. Okay. Now we will apply consistency equation. So what will be the consistency equation? That the theta at H with respect to AB will be equal to theta at B with respect to BC, but the direction will be in opposite sense. So negative will come into picture. So your consistency equation will look like this. Suppose this is your deflection and the slope here is like this. And this is your theta BA. This is your theta BC. And finally, you will get theta BA plus theta BA dash bar will be equal and opposite to theta BC plus theta BC bar. Okay. So if you substitute all the values, what you will get? You will get MA LAB upon EI plus 2 MB LAB upon EI plus LBC upon EBC IBC plus MC LBC upon EBC IBC, and that will be equal to minus of 6 into AAB, that is the area of that span, multiplied by the distance, that's AB, divided by EIL. Similarly, for span BC, it will be 6 ABC, that's BC, divided by EBC, IBC, LBC. So this is your complete three moment equation. Also, variation will occur when there is sinking of support. So in this case, we have not considered the sinking of support. So if sinking of support is there in the picture, then how this equation will differ, that we will see later. So what will happen when there is relative sinking of support in this structure, and then how moment or this three moment equation can be utilized, we will see in the coming questions. So let's solve a problem related to this. So suppose you have a beam, okay, with hinge. Let me draw hinge. Yeah, hinge at point A, roller support, again roller support, and in between you have a concentrated load of 20 kilonewton. Here the uniform load will be acting over the length, whole length. Okay, so this will be 7.5 kilonewton per meter, and the length of this whole beam is having each span of 3 meter. So 1.5 meter of this span, and this whole span will be 3 meter, and next span will also be a 3 meter span. Okay, and EI for all the members is same. So if EI for all the members is same, we can cancel it out on the both sides, and then what we will get? So let's start it. So here in this question we will get ds equal to 1 2 3 4 5 5 minus 3, so your ds will be 2. So that means you have to take two redundant forces. So provide hinge at B and C. So now our structure will be determinate. So now we will be having this point load. So due to this point load, we will be having the triangular bending moment, and due to this UDL, we will be having the parabolic bending moment. Okay, so their values will be 45 upon 3, that is 15 kilonewton meter, and here the maximum value will be due to WL square upon 8, and it will be also be 8.4375 kilonewton meter. In this, the area will be AAB, and let this area will be ABC. MD will be equal to 0. MA is also equal to 0. Now you are interested in only B and C. Okay. So here your AAB, how you will calculate? It will be 1 by 2 into 15 into 3 and that will be equal to 22.5. Your ABC will be equal to 2 by 3 into L into what is the total height? It is 8.4375, and that will come out to be 16.875. In this, your HAB, since the loading is symmetrical about the span, so it will be at the center. It will be HAB will be 1.5 meter, and your HBC, since this loading is also symmetrical, so that will also be 1.5 meter. Okay, so now we will apply the three moment equation. So apply three moment equation at joint B. Okay, so it will be MA LAB plus 2MB LAB LBC plus MC into LBC, and that is equal to minus 6 ABHAB upon L and minus 6 ABC HBC divided by LBC. Okay, substituting all the values. Now what we will get? We will get here 3 into MA plus 2 MB. L and L is 6 plus 3 into MC is equal to 6 into AAB is 22.5 into 1.5, and their total L is 3, and minus 6 into 16.875 into 1.5 divided by 3. So here MA is equal to 0. So if we solve the whole problem and rearrange it, we will get it as 4MB plus MC. It will be equal to minus 39.375. So this is our first equation. Now we have to require another equation also. So we will apply again the bending three moment equation at joint C. So apply three moment equation at joint C. What you will get? You will get uh, first is MB. So it will be 3MB plus 2MC into 6 plus 3MD minus 6 into 16 point, why it is not removing, 16.875 into 1.5 divided by 3. This is for span BC. Now span CD, there is no load acting, so that will be equal to 0. So in this, MD is also equal to 0. So what is the final equation we'll get? On rearranging, we will get 3MB plus 4MC. It will be equal to, let me see this. If we take 3, it was 16.875. So it means 3MB will not be there. Only MB will be there. MB plus 4MC, it will be equal to minus 16 0.875. So this is your second equation. Now on solving 1 and 2, what you will get? You will get MB equal to minus 9.375 kilonewton meter and MC equal to minus 1.875 kilonewton meter. So now we will take one span, that is span AB. So that means using, sorry. So applying sign convention, you will get BY and MB like this. Your 20 kilonewton force will be at the center and you will get AY and AX here. Fine. So now apply summation of moment about B equal to 0. So what you will get? You will get minus MB minus load is also anti-clockwise. So it will be 20 into 1.5 plus AY into 3 equal to 0. So by this you will get AY, and after substituting the value of MB you will get AY equal to 6.875 kilonewton meter. Now if you will take summation of moment about C equal to 0, you will get dy equal to minus 0.625 kilonewton meter. Alternatively, you can also determine dy using summation of y equal to 0. So if you take summation of y equal to 0, and then also you can determine dy. Okay. So now let's draw the bending moment diagram for this whole figure. Let me take this figure. Uh, Suppose this is our figure. Now if we apply, we will not apply, we will just draw the bending moment diagram. Yeah. So this is our beam. So in this is the, I think I have to make it again. So this is what we have got for the concentrated load. And then for the UDL, it will be like this. Okay. Now you have to define the moment that you have calculated. So that is MB. MB is around, MB you have calculated minus 9. So it will come here in between, and then MC is minus 1.8. It will come it around here. So if you make here like this, and this, yeah. So now this is our, the shaded region will give bending moment diagram of the beam. So this is your bending moment diagram for that indeterminate structure. After considering the value of MB and MC in the structure, how you can derive the uh, bending moment diagram for the undeterminate structure. So this is how you apply the three moment equation for an indeterminate structure. In this week also we have utilized the concept of method of inconsistent deformation for beams using unit load method. So let's solve some problems related to that also. So let's see the problems. So first problem is you have to let me read the question first. Shown below is a statically indeterminate beam. Solve using the unit load method. Let the redundant be VB. Let VB equal to H1. Now remove the redundant VB to obtain the statically determinate beam that is a primary structure. Now calculate the deflection at B of the primary structure where EI is constant throughout the structure. So in this, what they have said that this is your redundant. Remove this redundant and then solve the problem. Okay. So this is not the complete problem. This is just a part of the problem. I will tell you the procedure to solve the whole problem after solving the first three questions. Okay. So let's move patiently. So in this question, what you have to do, you have to remove the redundant and then determine the values. So suppose this is your M. Okay. So what will be the bending moment diagram? The bending moment diagram will look like this. This is negative because hogging will occur and it will be equal to M upon EI. So this is your M upon EI diagram. So in M upon EI diagram, anywhere you have, if you have required to calculate the deflection of beam, so use moment area method. What moment of area method says that the moment with respect to that particular point of the structure will give you the deflection at that particular point with respect to the another end. So here your vertical displacement at B will be equal to, so first we will write the area of this bending moment diagram, M upon EI into L and L by 2, and it will be acting at a distance of L by 4. Okay, so your moment will come out to be minus ml square upon 8 EI. So since this deflection is coming out to be negative, so that means upward deflection is occurring. Okay. Now, what the next question says us that in order to solve the problem using solve the beam using unit load method, you need to solve for H1 in the equation where delta B is the deflection for the at B due to primary structure and H1 is the redundant force VB and calculate the flexibility coefficient. So in this case, if we are required to calculate the flexibility coefficient, what we have to do? We have to take the beam, apply unit load where the redundant deformation is occurring, and then calculate the vertical displacement at B for this unit load. So vertical displacement for unit load. So for this case, we already know that it is PL cube upon 3EI. So that will be equal to L cube upon 3EI. And this is occurring in upward direction. Okay, so this is your F11. Okay, so now your next step is to utilize this consistency equation and determine the value of x1. Okay, so use this equation, that is delta B plus F11 into H1 is equal to 0. So you have delta B equal ml square upon 8 EI plus L cube upon 24 EI. Oh, sorry, I think I have done wrong here. So in this, our length is L by 2. Okay, okay. So this is our L by 2. So L by 2 cube upon 3 EI. So you will get here it as L cube upon 8 into 324 EI. And that will be in upward direction. So this will be your F11. Now this will be L cube upon 24 EI into HI equal to 0. So now your HI will be equal to minus ml square upon 8 EI into 24 upon EI divided by L cube. And from this you will get minus 3m upon L. Okay. Or if we take minus here, this will be plus and this will be plus. So H1 will be your in upward direction. So let me summarize this, then it will be easy for you to understand this. So first of all, what this equation tells you. So this equation tells you that the deflection at point B should be equal to 0. Okay, so that means delta B, so it means the total delta, let me write it like this, total delta at B will be equal to 0. So here the deflection will come out from the two things. One is due to determinate structure and another is due to the redundant force. Okay, so from determinate structure, what you have calculated it as delta B. From redundant force, since you are applying the unit load method, so this is your unit, this is your displacement due to the unit force. So when you multiply by it by total force, so you will get the deflection due to the total redundant force that is applied. So so all whole this equation should be equal to 0. That's why delta B plus FII 1 plus H1 is equal to 0. This is the whole concept behind this consistency equation. Okay. So what is the steps that we have followed to solve this problem? So suppose any indeterminate beam is given to you, you have to take a redundant force. So what you will do, you will remove this redundant force, make the structure as determinate structure. Then you have to find the displacement at the point where the redundant force is applied. How you will do? You will do using moment area method, and then you will find the vertical displacement at that point. Then what you will do to define or determine the value of flexibility flexibility coefficient at that particular point, you will apply a unit load at that redundant force, and then you will determine the vertical displacement due to that. And after determining the vertical displacement due to the unit load, you will use the consistency equation and derive the value of x1. And this x1 is equal to your VB. Okay, this is how we will solve the problem. So now let's solve again the problem, next problem. Then might maybe the concept will be clear to you. So again, this is an indeterminate structure given to you, in which they have mentioned that this support is redundant. So let me read the question first, then it will be easy to understand. So shown below is a statically indeterminate beam. Solve using the unit load method. Let the redundant be By. So it means this is redundant. So let By is equal to H1, that is there in our equation. Now remove the redundant force and obtain the statically determinate beam, that is the primary structure. Now calculate the value of vertical displacement at V, that is dl1 of the primary structure, considering EI to be constant throughout the structure. So if you make this whole structure as remove this support at point B, so your bending moment here will be cubic parabola. It would be like this. No, it will not be straight line. It will be cubic parabola. Okay, so it will be like this. And what will the value of maximum value of the bending moment here? It will be equal to 1 by 2 area. First is area 1 by 2 into W into L, and it is acting at a distance of L by 3. So it is WL square upon 6 EI, because this is M by EI diagram. And this will be negative. Okay, so to determine the vertical support, or sorry, vertical displacement at support B, how you will do? You will take the area of this diagram. So that will be equal to 1 by 4 into base is L, altitude, that is WL square upon 6EI, multiply by the centroid, and it is at a distance of L by 5 from B. Okay, so your value comes out to be WL power 4 upon six five so 30, 30 into 4, 120, 120 EI. Okay. Oh, sorry. So this will be, I think, 4L by 5. Yeah, 4L by 5. Then you will get the value here as 30 EI. Now it is fine. Okay, so your DL1 comes out to be WL4 upon 30 EI, and this value is approximately equal to when you have a uniformly varying load for the fixed beam, and the maximum deflection, maximum moment, sorry, and the moment at the end B, how it will come as, it will come as WL cube upon 30 EI. So means it is somewhat related to that thing. So now what you will do in next question, in this you have to calculate the flexibility coefficient for the this beam. So what is written in the question? In order to solve the beam using unit load method, we need to solve for h1 in the equation. So how you will solve for the h1? You will calculate the value of flexibility coefficient for the beam mentioned in question 4. So how you will do? So what we will do, we will apply a unit load in this beam. So here the deflection is negative. Negative means upward. So we will apply a downward load. Okay. So here the value of F11 will come out to be PL cube upon 3EI, and that will be equal to L cube upon 3EI. Now in next question, you will are required to calculate the vertical reaction for the fixed support as well as for the roller support. So it means you have to calculate the vertical reaction using this consistency equation. So your consistency equation given here is dl1 plus f11 h1 equal to 0, and your dl1 is equal to minus wl4 upon 30 ei plus f11. F11 is l cube upon 3 ei into h1 equal to 0. So your h1 is coming out to be equal to wl4 upon 30 ei into 3 ei upon l cube, and that will be w upon 10. This is your by. Okay. So to determine the value of next thing is we have to calculate ay also. So how we will calculate? We will take summation of forces equal to 0. So summation of V will be equal to 0. That means our AY plus BY will be equal to WL by 2. Okay. So it means your AY will be equal to WL by 2 minus WL by 10. So this value will come out to be 8L upon 20. So 4L upon 10, 12 by 5 to WL upon 5. Okay. Um, Now it is okay. So this is the whole concept, that how you will solve the problem of indeterminate reaction that are you are required to calculate for the indeterminate beam using the unit load method. Okay, so let's move to the next question. Next question is also similar to what we have done. So in this question, they are mentioning that this force should be redundant. So if this should be redundant, so it means your beam will have this thing. So this will be the 50 kilonewton force. This will be 50 kilonewton force. So your reaction will also be same because it is a symmetrical beam. And this the sagging moment occurs, so it will be m upon ei, positive bending moment diagram. And there the value will be 6 into 5, 30 upon ei, 30 upon ei. So your vertical displacement at B will be equal to delta B 1 by 2 into 6 into 300 upon 300. Oh, sorry. 15 to 6, 300. 300 upon EI. What is the distance? Distance will be 6 by 6 plus 6 by 3. Total 8 plus 300 upon EI into 6, acting at 6 by 2. So your delta B will come out to be, so this value will be 7200 upon EI plus 5400 upon EI, and delta B will become 12,600 upon EI, and it is positive. So it means how we have written, when displacement is coming out to be negative, so it is upward. Here displacement coming out to be positive, so it will be downward. Downward displacement we have considered to be positive. Now we are required to have upward deflection. So for this, apply unit load at the point where redundant force is considered. So your reactions at the end will be 0.5 and zero point 0.5. If you draw the bending moment diagram for this structure, you will get it like this, and the value will be 6 upon EI, and this will be negative bending moment. So here your F11 will be equal to 1 by 2 into 6 upon EI, and it will be at a distance of 6 by 3. And this, if we multiply by 2, because so what we will get? We will get it as 72 upon EI. Okay, and negative. Fine. Now we will apply the consistency equation, that is delta B plus F11 plus H1 is equal to 0. Delta B we have calculated is positive 12,600 upon EI plus what is F11, that is minus 72 upon EI into H1 equal to 0. So we'll get H1 equal to 12,600 upon EI into EI upon 72. So that will be equal to 175 kilonewton. This is our By. Okay, so this is how we'll solve the problems for unit load method or method of consistency deformation for beams. Okay, fine. So last question for today is, if we are required to calculate the moment three moment equation and there is sinking of supports. So if there is sinking of supports, so we will apply three moment theorem. So in this, Here for span ABC, your three moment will be 2 into, sorry, MA into 4, but that will be equal to 0, plus 2 into MB, 4 plus 3 plus 3 into MC, and that is equal to minus, not say, minus 6E into relative displacement. So relative displacement will be 5 minus 0, that will be 5 upon 1000 upon what is the length? 4. And here the relative displacement is C is sinking by 10. So 5 minus 10. So that will be minus 5. Okay. If we solve the problem here, MA will be equal to 0. And what you will get? You will get 14 MB plus 3 MC equal to 6 plus 80,000. So 80,000 how will get? Because here also I is there. Upon I is there. So EI we have written as 80,000. 5 upon 4,000 minus 5 upon 3,000. And that will be equal to 6 into 80,000 into minus 5 upon 12,000. So finally, you will get 14 MB plus 3 MC minus 200. So this is the first equation that you have got. So in this question, it is only required to calculate the three moment equation for the span ABC. So if you are required to calculate the moment MB and MC, what you will do, you will take another three moment theorem for span BCD and apply the three moment theorem at joint C. So again, you will get the values in connection with MB and MC because MD is also equal to 0. MD is equal to 0. Okay. So then if you solve that two equations, you will get the value of MB and MC. And since there is no external load, you substitute all the values in the diagram, and then you will get to know the value of bending moment diagram also. So this is what we have covered in this week, starting with we have seen the problem related to three moment equation for external loadings applied over the length of the beam and how you will solve that problem, and based upon that how you will determine the bending moment diagram for that continuous beams. And later on we have seen if you have uh, indeterminate beams, then how you will determine the value of unknown reactions. So in here what we have done, we have first remove the remove the indeterminacy or redundant force that is there in the member. Then we have applied the unit load at the point where redundant force is considered, and then with the help of consistent equation we have determined the value of unknown or redundant reaction at that particular point. So let's have a recap that what we have covered today is We started with the how to solve the problem of consistent deformation, wherein we have to determine the degree of indeterminacy, then select the redundant force, solve for determinate structure, solve for redundant force, solve for the structure with the redundant force, and then apply consistency equation and get to know the value of unknown reaction at that particular point. So for the three moment equation, what we have done, we have taken a continuous beam with variable loadings that are acting over it, and then using the moment area of area method, we have compared the rotations at along the different points of the beam, and then we have got to know the journal equation for the three moment equation. So this is the problem that we have solved for the three moment equation, and we have applied the three moment equation both at point joint B and joint C. Using that, we have got two equations. From two equations, we got the two values of MB and MC, and based upon that, substituting the bending moment diagram for external or for the external loading as well as for the internal MB and MC that we have got, finally we will determine the bending moment diagram of the whole structure. Then we have solved the problem for method of consistent deformation for the structure, wherein first we will remove the redundant force, then solve for the vertical displacement using the moment area method. Then we will remove all the external loading, provide a unit load at the point where redundant force is considered, and then again we will calculate the vertical displacement for the unit load, and we will call this as a flexibility coefficient. Because what is the definition of flexibility? It is defined as the deformation produced under unit load. So that's why unit load is if applied, the deformation that is obtained is the flexibility coefficient. Then we will apply the consistent equation, and solving the consistency equation, we will get to know the value of unknown reaction at that particular point. Similarly, we have solved the problem for this uniformly varying load to determine the value of By and Ay along the various along the support of this beam element. Then again, to determine the value of VB, we have applied the this unit load method, and based upon that, we have solved the problem and determined the value of By on the beam element. Finally, we have done another question for the three moment theorem, and in this there is relative displacement of the supports, and to determine that, we have applied the equation and determine the value on the equation for the span ABC. If we again solve the question and try to determine for the values for the span BCD, we will get to know the value of MB and MC using when we solve the two equations, and then we can plot and get to know the BMD for this whole week. So this is what we have covered in this whole week. So till now, what we have covered. So we have covered till this point. That is, we have covered the method of consistency deformation. So the only topics that are left for this course is to solve the statically indeterminate structures for beams and frames using moment distribution method, slope deflection method, and then we will give you a brief introduction to the direct stiffness method. So problem related to what we have covered in this week 9 are shown to you. If you have any problem, you can contact us from the structure from the discussion forum in the Swayam app that is available with you. The TAs will try to respond for your query as early and possible, and hope you have liked this session. May you try to solve as much problems as you can, so that your doubts will get uh, covered when you solve any problem related to the structures. Okay, so have a nice day. uh, Enjoy your weekend.